So once again, a big welcome to everyone who's joining this 68th edition of the virtual seminar on precision physics and fundamental symmetries. It's really my great pleasure to introduce today's speaker, Eric Cornell, someone whose outstanding work will be familiar to a great many people in the audience today, covering both precision physics, penning trap physics, ultra-code atomic physics, and precision tests of fundamental symmetries. Eric undertook his PhD studies with Dave Pritchard at MIT, conducting mass comparisons of molecular ions in penning traps with 40 parts per trillion precision. As part of this work, he developed new frequency measurement techniques known collectively as the phase methods, which form the basis of many of the most precise measurements in penning traps today. After his PhD, Eric moved to JILA, where he famously worked with Carl Wieman to achieve the first Bose-Einstein condensation using rubidium atoms in 1995. Carl, Eric, and Wolfgang Kettle would later share the 2001 Nobel Prize in Physics for creating and studying atomic BECs. BECs are now used the world over to study quantum many-body physics, quantum simulation, sensors for gravity, rotational magnetic fields, and all sorts of other exciting applications. And a BEC has even been created in space on the International Space Station as part of Jet Propulsion Laboratory's Cold Atom Lab, a project in which Eric is also involved. So not content with revolutionizing two fields of physics, Eric leads efforts to measure the electron-electric dipole moment using molecular ions, a subject which he'll talk about today. Eric's group at JILA are at the forefront of performing these extremely challenging measurements which give unique insights into new P and T violating physics. I was really heartened to hear some advice, or to read some advice that Eric reportedly gave his students, which is pay attention to the physics going on around you, go to the departmental colloquium, even if it's not your thing. One of the keys to success is making connections to things that maybe others haven't seen. So I hope we're able to make some connections today. And with that, Eric, the floor is yours.
Okay, well, thank you so much, Jack. That's a very generous introduction. We're going to be talking about the electron-electric dipole moment. And I think in this seminar of all seminars, I don't need to spend a lot of time motivating a measurement of the electron-electric dipole moment, but very simply, like so many precision measurements, we are trying to look for physics beyond the standard model. And the standard model prediction for the electron-electric dipole moment is unobservably small, 9 orders of magnitude smaller than the current limit. So, and an electron-electric dipole moment measurement is therefore a background-free search for new physics. We don't have to subtract out the standard model prediction for any non-zero value we should happen to see. If we look out into the universe around us, we see matter and not antimatter, and this tells us there must be, looking backwards at some points, at least CP violating physics not contained in the standard model. And that same physics will, at least at some level, very likely lead to EDMs and currently known particles. And thus an EDM search has a non-vanishing probability of actually seeing something not zero. Or at least we tell ourselves that as we go about our daily work. Here's a picture of the group, and I just want to flag Jun Yi. Professor Jun Yi and I have worked together jointly as advisors for this project now for more than a decade. And then I'll just also flag the three most senior people in the lab, Tanya Rusi, Dr. Luke Caldwell, and Xiaobun Ng, who are leading the laboratory effort on these experiments. More students include Sunil Park, Anzhou Wang, Trevor Wright, and Noah Schlossberger, and we're very grateful to our funders, and we also have a good interaction with a number of theorists, both at JILA and away, John Bohm, Bob Field, Chris Green, and as far away as St. Petersburg. So it's an international effort. So here's the electron. It spins, it's got a mass, it's got a charge. If it's spinning, it's got a magnetic dipole moment, therefore a north and south pole. Possibly, in addition to this, it will have an electric dipole moment, which you could think of as a little extra positive charge near the North Pole, a little extra negative near the South Pole, or vice versa. And you can think of this positive charge as sort of interacting destructively with the monopole, and the negative charge is interacting constructively with the monopole. So in a charged particle, an electric dipole moment is very much similar to saying the center of charge is offset from the center of mass. And you can just express that, therefore, in units of length, of centimeters, say. If this effect exists, it violates all sorts of things that aren't often violated, and we might want to get a notion of how big might this be? What it would be? It's a length scale. What's a reasonable guess for a length scale? Electrons have built into them, because they have charge and mass, they have a various length scales associated with them. The most simplest one maybe to think about is if you have an electron and it's spinning around a single charged particle, a positively charged particle, then the sort of lowest order electric dipole transition moment, so it's an electric dipole moment of a transition between two states of opposite parity, is just the Bohr radius, right? Half an angstrom or something. Down from there is the magnetic dipole moment. I'm an old enough guy that when I learned electricity and magnetism, we learned about magnetic dipole moments also of having units of length. And they're smaller than the electric dipole transition moment by a factor of the fine structure constant. That's called the Compton radius. In my units, the Compton radius is basically the magnetic moment of the electron, the Bohr magneton. One more factor, we go down one more factor of the fine structure constant, we get the classical radius of the electron. You can think of this simply as if I took one fundamental unit of charge and squeezed it down to a ball. As it gets smaller and smaller, there's more and more Coulomb repulsive energy. And when that repulsive energy, I can think of that as equal as an mc squared. I can think of express that repulsive energy in terms of the rest mass. If I think that's where the rest mass of the electron is coming from, then that gives me another length scale, which is sometimes called the classical radius of the electron, and it's just a couple Fermi, about the same size as a proton, really. This is not particularly relevant for this talk, but since we are thinking about particle physics, the shortest length scales, which you can sort of see in an accelerator, basically sort of more directly by a scattering experiment, is given by the wavelength of the particles zooming around in the LHC, which is yet smaller. The current limit of the electron-electric dipole moment is it hasn't been seen. Now, all measurements so far have been consistent with zero. The ACME group at Harvard and Yale, and now at Northwestern and Chicago, say that it's less than 10 to the minus 29 centimeters. So and we hope to do that well or better soon. There are 16 orders of magnitude between the classical radius of the electron and the current limit. What does that 16 orders of magnitude buy us? We can make a very simple sort of general Feynman diagram where we imagine that in the electric dipole moment Feynman diagram, there's a loop that includes some new physics. I call it smooth physics just because this is a very old slide. It used to be everyone liked supersymmetry and all the particles started with S. And on very general principles and with a lot of simplifying assumptions, you can get a notion of what a new particle or a family of new particles like that would give to an electric dipole moment. And it's basically compared to this classical radius, it's down by a sort of unknown mixing angle and by this ratio of the electron mass to the new particle's mass squared. So if we assume some sort of naturalness, and say this is maybe an angle of about 1, then by the time we're down to 10 to the minus 29, there's a lot of assumptions that go into this where we should be sensitive to new particles on the order of 6 TeV. And that should be compared with sort of the most typical particles which are detected at the LHC, which are usually a few hundred GeV. So there's a lot of sensitivity here. We hope to do better yet, and therefore be sensitive to still more massive particles, hypothetical massive particles. How do we measure an electron EDM? Well, we could ask ourselves, how do we measure a magnetic dipole moment of an electron? That's just electron spin resonance. We take an electron, put it in a magnetic field, shine a radio wave at it, the electron flips over, and there's a preferred frequency that causes the electron to flip over, and that preferred frequency is just exactly at the magnetic dipole moment times the magnetic field. If we now imagine that the electron has both a magnetic dipole moment and an electric dipole moment, and if we apply an electric field parallel to our magnetic field, it shifts the resonance. We change the direction of the electric field, it shifts the resonance the other way. We take the difference in the center of those two resonances, the magnetic moment drops out, and what's left is a pure measurement of the electric dipole moment times the effective electric field that we apply to the electron. Okay, so now we want to make a really good EDM measurement. The time has gone where you can make a bad one. If you want to be interesting, you'd have to make a good one. What goes into making a good electric dipole moment experiment? First, you need a really big electric field to split those two lines, even in the presence of, you want a big electric field so that you get a splitting even in the presence of a small electric dipole moment. You want to have long coherence lines, which makes these resonance lines narrower and therefore easier to distinguish one from the other. And then you want to do better than just look at the compare these lines within their line widths. You want to find the center of their lines. And if you do things in a sort of relatively low noise way, you can statistically find the center of these lines to something about equal to a fractional width, which is given by the square root of the number of electron spin flips you can actually distinctly detect at the shot noise limit. And so you have a combined figure of merit, which has got, you want big electric field, long coherence times, and lots of counts. So the problem is if you apply a big electric field to an electron, the electron flies away. So the solution to this, which was originally introduced by Pat Sandars in the 60s, is don't work with a bare electron, attach it to a big atomic nucleus. You actually get a relativistic enhancement associated, which is proportional to the z cubed of that electron, of the nucleus. And also the thing is heavier, so it doesn't move around and it's neutral. We actually use not only a large Z nucleus, but we attach to it a fluorine molecule, which is just basically take any atom, and you can, almost any atom you care to name, you can attach a fluorine molecule to it. And that's sort of nature's way of applying a very large electric field to an atom, or in this case, via the next order process to the electron itself. So even though we apply only about order 10 volts per centimeter in the lab, but that can polarize the molecule, and the effective electric field applied to the electron is larger by order of 9 orders of magnitude. It's an electric field amplifier. Also, we want to have long coherence times, so we work in an ion trap. In principle, you could put a neutral molecule and do experiments on neutral molecules. And in fact, people are working on doing this, doing experiments on looking to do EDM experiments on neutral molecules. But right now, trapping neutral molecules is hard. And by the time you finish trapping a neutral molecule, you're tired and you don't have enough energy left to do a very difficult precision measurement experiment. On the other hand, trapping a molecular ion is really easy. I was trapping molecular ions in the 1980s. That was a long time ago, and it wasn't very hard then, and it's not very hard now. So we will, instead of working with neutral molecules, we work with ionic molecules. But anytime you have an ion trap or any kind of trap, you're going to have time varying, spatially inhomogeneous fields, and that doesn't sound on the face of it like a good place to do a precision measurement experiment. We steal a great idea from Dave DeMille, who pointed out that if you work with a class of molecules that have a so-called omega equal 1 or higher, then molecules like that have a given rotational level will have two closely spaced states of opposite parity, corresponding to the molecule reaching one way and the other way in either a symmetric or asymmetric combination. And then you need to apply a relatively small electric field to mix those two states and polarize the molecule. And then, for instance, so this is a J equal 1 state, which is the lowest rotational state of a molecule which has omega equal 1. Then you have a structure that looks something like this. And if you apply a magnetic field that interacts with the magnetic moment, say, of the electron, and shifts the levels to these blue positions. And then finally, if you look here, you can see that here's the electron, here's the internal electric field, here's the electron, here's the internal electric field. These four things get shifted in opposite directions if there is an electric dipole moment, which means if you were to measure this two photon transition energy, this upper one indicated in orange, and this lower one also indicated in orange, and you subtract the two, magnetic field effects drop out, the stark shifts of the molecule itself drop out, and all that's left is the electric dipole moment, electric dipole moment of the electron times some internal electric field in the molecule. So it's a very powerful technique. And you notice that what does not appear in this expression is the amplitude of the ambient magnetic field or the amplitude of the ambient electric field. So even if you're in a very inhomogeneous environment, you can make a very quiet measurement. We do Ramsey spectroscopy. So we take the atom start in one of these states, we apply a pi/2 pulse, they evolve for a little while, we apply another pi/2 pulse, and then we measure the population in one state or the other, classic Ramsey spectroscopy. And we actually are able to do it simultaneously in both the upper and lower states. We have a way of detecting the population of this state and then separately detecting the population of this state. So we actually do the experiments on an incoherent mixture of atoms in the upper level and atoms in the lower level, it's the coherence is between the delta m equal 2 transition and not between the Stark levels. Here's a Ramsey fringe. This case, you can see there's a little break here. This goes from 0 to about 700 milliseconds. We're currently operate almost out to 3 seconds now, much longer coherence times than this picture indicates. And this basically is just the probability of finding the molecule with electrons spin up or spin down after some length of time. And in this particular case, we're looking at a frequency of about 20 hertz because it's a very small, the bias field we apply is quite small. And you can see that, yeah, so you can see that we basically, usually we just take measure a Ramsey fringe with relatively short spacing between the pulses. This is the spacing between the pi over 2 pulses. And then we measure another Ramsey fringe with relatively long spacing. And basically this sort of nails down what the original phase of the superposition is. And this tells us what the final phase of the superposition is. And the difference in phase divided by this time is just the frequency, an angular frequency. That's what we measure. So we do need to apply an electric bias field to the ion, not a huge one, but a few volts per centimeter in order to apply it. We're working in an ion trap, and almost the definition of an ion trap is the definition of the center of an ion trap, where the ions want to go, the lowest point of the potential in an ion trap. The electric field there has to be 0. If the average electric field there wasn't 0, the ions would move somewhere else. So how can we, in an ion trap, how can we polarize the ion? So we need to apply an electric field to polarize the molecule and define a quantization axis. But if the molecule is charged, then when we apply the electric field, the molecule will fly away. So how do you apply an electric bias field to an ion? And the answer is you use a heavy ion storage ring. Here's a large heavy ion storage ring. And if your ion is going at a very fast rate around this circle, there are magnetic fields which cause it to bend, but the effect from the ion point of view, it's basically seeing an electric field which is always pointing inward. So yes, you have to operate in a sort of moving and rotating frame, but you could do it, principally, you could do an electric dipole moment in a big storage ring like this. I love this idea, but this is a long commute for me. I don't like plane rides. So I thought about building something like this near my own university. Here are the Rocky Mountains of Colorado. And we thought we could build this storage ring in Boulder. It would pass, here is the physics department here. The storage ring would pass underneath of the football stadium, which would require us to demolish the football stadium. But I actually saw that as a feature of the proposal. But the vice chancellor saw differently. He wouldn't let me build this. I thought, well, we could make a smaller one. No. What if we make a relatively small one, which would sit in the lawn, the grassy lawn where the students play Frisbee outside of the physics department, outside of JILA? Still said no. So we decided to build a really, really small ion storage ring. It's even hard. Here's a scale of it. We're going to zoom in. Our ion storage ring is about 1 millimeter in radius, and it's not really a ring at all. It's just a rotating applied electric field. So we apply electric field. It rotates in the laboratory, and in real time, the molecule quantization axis tracks the electric field. And we have to make that the rotation of that bias field is fast enough that the ion travels on a relatively small circle and doesn't go anywhere. The radius of this circle is a little bit less than 1 millimeter. And it needs the rotation rate needs to be slow enough that instantaneously the quantization axis of the molecule has no problem tracking this rotation. And then we have to do the spectroscopy in the rotating frame. And I'll be frank, there are complexities associated with doing precision spectroscopy in rotating frames, but we've spent 15 years understanding how to do it, and we're pretty good at it. Here's the current second generation ion trap. For scale, you can see these sort of planar pieces of steel here are separated by about 10 centimeters. And there's 8 of them, and we can apply different voltages on them. One gives us an oscillating quadrupole electric field, which provides transverse confinement. And another set of another frequency causes a very uniform rotating electric field. These electrodes are designed so that the higher order terms drop out, and the rotating electric field is quite uniform in magnitude. And we can provide this is the axial direction of our Powell trap, and we can provide this little plate down here is charged positive, and a similar one up here is charged positive, and that provides the axial confinement. This whole thing goes into a vacuum chamber, and we shine lasers at it. here's a conceptual design of the experiment. The ablation laser melts a little bit of hafnium. We also have experiments where we use thorium. We let in a little bit of gas, which contains some fluorine. In our case, it's mostly argon, but a little bit of sulfur hexafluoride. Chemistry happens. We have neutral hafnium fluoride. It travels at about 1 kilometer per second. And when it gets to exactly to the center of our ion trap, we photoionize it and then apply some electric fields to stop the motion. Stopping a rapidly moving neutral molecule is difficult. Stopping a rapidly moving ionic molecule, it just takes a couple op amps that you turn on and off. It's a relatively small electric field, a few volts per centimeter, and it comes to a stop. We have many lasers coming in, which do the state preparation and readout. And then the final detection of the spin is done by a contingent process. If the electron spin is flipped or not flipped after a higher order resonance process, the molecule either dissociates or it doesn't. And when we dump the ions onto a detector, we see sort of early and late arrival times corresponding to molecules which have dissociated and molecules that haven't dissociated. And it's that ratio which gives us sort of the amplitude of our Ramsey fringe. This just shows more of the laser thing. We do some optical pumping. Hafnium fluoride plus is not well designed for, it doesn't have ideal Frank-Condon overlaps, so you can't really do laser cooling, but you can do at least some modest amount of optical pumping with relatively inefficiently, but you can concentrate the population in a particular rotational level and even a particular Zeeman level, which we do using polarized laser beams. Unfortunately, we're not able to detect the very low energy 100 hertz photon that corresponds to the electron spin flip. So after we've done the Ramsey spectroscopy, we come in with a depletion laser, which is circularly polarized, and only the molecules which have not had a spin flip are removed. The ones that remain in the state are then subject to a 2-photon photodissociation pulse, excites the molecules to a repulsive potential, molecules fly apart. And then, as I said, right after we do that, we apply electric fields to dump the contents of the trap onto a detector, and we see pulses that arrive early or late, and we're able to read out the spins this way. Very complicated experiment. There are many, many lasers. 4 separate wavelengths of ultraviolet photons come in, and I think 6 separate wavelengths of infrared photons. It's a beast of an experiment. We've been working on it for many years, but we've got it pretty well debugged. Here's the Ramsey fringe, and you can see our actual signal here involves, here's the undissociated hafnium fluoride plus molecules and a relatively small fraction of hafnium ions that arrive sooner. And basically, it's the area under that of the hafnium ions arriving earlier, which basically maps directly into the y-axis of this plot. And then the x-axis of this plot is just how much time has evolved between the Ramsey pulses. Experiment is a giant room full of lasers, and you can see at the very back, or maybe you can't, there's a vacuum chamber that supports our arrays. It's worth comparing our experiment to the what I would call the other lead experiment in the world of people looking for electron-electric dipole moment. In fact, the Acme group has by far the best measurement right now. In many ways, we're quite similar. We use a heavy metal fluoride molecule, which gives us a big electric field. So does Acme. We use ions, which means we can trap them for many seconds, but we can't trap very many of them because ions have a strong collisional process between them, and there's space charge. Acme uses neutrals. They have a much larger count rate. They don't have to worry about space charge. So their signal to noise in terms of like finding the edges of their fringes is much higher, but their line widths are much broader. I find it somewhat strange that, in fact, our overall sensitivity between the two experiments is really quite similar. These two effects more or less balance each other out. We have very narrow lines with low signal to noise. They have very broad lines with high signal to noise, and it comes out to almost the same sensitivity per root hour. We have to work in a rotating frame of reference, whereas this is a beam, which is a simpler thing to do. By the way, coming soon, or maybe not so very soon, there are going to be experiments using trapped neutral molecules. For instance, Nick Hutzler's group at Caltech is working on this. This question of whether you want to have a narrow line with bad signal to noise or a broad line with good signal to noise. There's a lot to be said for having a narrow line in terms of rejecting systematic errors. There's really two kinds of systematic errors on a Ramsey experiment. You could call them like phase errors and frequency errors. Typically, you'll take a Ramsey fringe at early time, you'll wait a long time, you'll take a Ramsey fringe at late time. You can think of this fringe, basically we fit this with a sine wave and we determine the phase of a zero crossing here. We wait, there's a little gap here, we wait, this shows 700 milliseconds. These days we wait sometimes as long as 3 seconds. And we measure the phase here. And so we are sensitive to phase errors. So if there are readout errors, detectors are saturating, line shape problems, problems with the polarization of our lasers that are doing the optical pumping, that will move the phase of this a little bit, or it might move the phase of this a little bit. But if there's a long time in between them, if you have a long coherence time, a change in the phase here becomes a change in the frequency only after you've divided by that time. So this is a very long time. A phase error here is relatively small frequency error. So the phase errors get better if you have long Ramsey times. There's also what I would call true in the dark frequency errors, which occur when you are not in between the 2 pi over 2 pulses. There's these phase errors tend to be very technical. They tend to be specific to your experiment. They have to do with birefringence in your mirrors and things like that. The in the dark frequency errors are much more readily modelable. You model them using Maxwell's equations as opposed to having to understand the material properties of your mirrors or something like that. These we have to deal with, but these we're relatively immune to because we have very long, not fully immune, because we have very long coherence times. It's worth sort of comparing. The original sort of god of electron EDM was Gene Cummins, the late Gene Cummins, who his experiment, his career culminated with a 2002 measurement in thallium. Thallium was not a molecule, so its internal electric field was relatively small compared to molecules. It was a beam, so he had short coherence times. And he claimed a final accuracy, not his upper limit, you understand, but the 1 sigma precision on his experiment of 7 times 10 to the minus 28. To make a claim like that, he was in effect saying that he thought that his phase errors were less than 0.3 microradians. Acme came along, and it made a measurement which was a factor of 20 better. And yet, even though it was a factor of 20 better, they could get away with doing less accurate measurements. In a certain sense, it's a less accurate measurement in terms of radians, microradians of precision, because they had a much larger internal electric field, which was larger by a factor of 100. As they got more and more accurate, they had to do better and better, but they were still weren't having to work as hard in some sense as Cummins. We have the advantage of having a larger electric field, but also a much longer coherence time, which folds right in. So for us, the kinds of angle errors we can understand, the phase errors we can accept, which don't hurt us in our experiments, in our Ramsey fringes and what have you, are much larger, which means much easier. You don't have to worry very hard to make a measurement which is good to just a little bit better than a milli-radian. Is not a heroic measurement in terms of the quality of your beam splitters or anything like that. So it makes, there's not all of our systematics, but many of our systematics are relatively easy to keep under control. We typically do simultaneous experiments measuring the upper level and the lower level. They oscillate, here's like a Ramsey fringe, which we characterize here by the zero crossings here, and maybe later, after some 200 milliseconds, maybe later these fringes are a little bit offset from one another because the frequencies might be a little different if there's electric dipole moment. And so we're looking sort of at differences in populations between the upper and lower state on one side of the fringe versus on the other side of the fringe. This sort of crisscross pattern here is the signal for an electric dipole moment. We actually measure many different Ramsey fringes with reversing the sign of the magnetic field, reversing the handedness of the rotation of the rotating electric field. We measure all these different frequencies and we combine them in a linear combination. If we have 8 different measurements, we can have 8 different orthogonal, linearly independent linear combinations of them, which we label. It's an in-house jargon similar to that used by the Acme group. Basically, label by showing like which of these combinations are odd and which are even. One of these, in our particular case, that right there, that frequency combination right there, is sensitive to the electric dipole moment. The other ones are sensitive to various experimental imperfections of the trap. And so we measure all of these frequencies and we use them to debug the trap. So for instance, to give you an example, basically the difference between these two, in our jargon, we call it FBD, but it's proportional to electric dipole moment. If we instead, so this would be if we averaged over the two rotational directions. If instead we sort of measured this difference with a clockwise case and the counterclockwise case, in our jargon we call it FBDR, but what we notice is that it's not equal to 0. It's a little bit like saying our measurement of the electric dipole moment depends on the direction that our trap is rotating, which sounds like that can't be right because that's not interesting. That's not fundamental particle physics. You can see here, this is many weeks of data down here, but you can see that the average of this of all this many weeks of data is distinctly different from 0. And that seems worrisome, but we understand what's going on. If instead of looking at the difference between these two frequencies, we look at the sum of these two frequencies and we see how that changes when we change the rotational direction, we actually see a very large effect. This is now in millihertz here. Sorry, still in hertz. So 200 millihertz, a very large, by our standards, an enormously large shift. And what it tells us is that there is a magnetic field in the experiment that is changing with the sign of rotation. And we know what that is. That's basically, in order to make the electric field rotate, we have to put voltages, time-varying voltages, onto the electrodes, and that involves time-varying currents flowing into and out of the electrodes. And those time-varying currents create a time-varying magnetic field, and some of that magnetic field tracks the quantization axis as it rotates. So we can use this to measure how big the rotation-dependent magnetic field is, and then we can make a correction because, well, it wouldn't even be a problem if the G factors of these two transitions were exactly the same. We wouldn't really care about the size of magnetic field because they're slightly different. We can correct the science signal that changes with rotation by the magnetic field that changes with rotation, corrected with a factor which is just proportional to the fractional difference in the G factor. And when we do that and we look at it, we see that we measure the same electric dipole moment, whether we're rotating clockwise or counterclockwise. So these are the sorts of things that we do and get very good at. There's another important effect of rotation, which is Berry's phase. I think many of you are familiar with this geometric phase. If you have a bias field, and the bias field over time changes a little bit, you sort of imagine that this is the electric field as our bias field, and it traces out a sort of conical shape. So the bias field, sweeps out some enclosed solid angle. No matter how slowly we go around, by the time we come back, we'll find out that if our particle is in and it has a particular spin inside projected along this, it'll have picked up a phase which is proportional to its angular momentum along the quantization axis times this enclosed area. So if we're trying to do spectroscopy between a spin up and spin down, there's going to be a difference in the delta phi, which is plus or minus m times this area. In our case, our electric field is actually rotating in the equator. Basically, the electric field is traced. The Lissajous figure is a circle, and it's rotating very rapidly. It's rotating at 300 kilohertz. So if it rotates at 300 kilohertz, and it's not making a little rotation like this, it's in the plane. So every time it goes around, it sweeps out a circle in the equator subtends an angle of 2 pi steradians. So if you work it out, it's hundreds of kilohertz worth of Berry's phase shift. But it turns out that 300 kilohertz times 2 pi is really just the same as 0 times 2 pi, because all phase measurements are modulo 2 pi. So the important thing is that we need to have the electric field just exactly in the equator and not pointing up or pointing down. If it were to point, if the electric field were to not be, if the Lissajous figure were not purely in the XY plane, but pointing a little bit up, the enclosed angle would be not exactly 2 pi, and we'd see very large frequency shifts. On the face of it, you might think this is not a good, the basic scale of the Berry's phase is 750 kilohertz, and we're trying to do 30 microhertz spectroscopy. What saves us is that for this Lissajous figure to be pointing up, there has to be not just a rotating electric field, but a static electric field pointing up to give us that sort of conical shape. We know there could be exactly 0 static electric field pointing up on average, because if there were a static electric field pointing up, the ion would move in response to that to a different place in the trap. The ion very, very precisely finds the place in the trap where the average axial electric field is 0. Otherwise, it would move somewhere else. And so we don't see much Berry's phase. So that's but we see some, and we have to understand it. One advantage of having a rotating bias field is that if we happen to have a little magnetic field, say you have some magnetic field which you didn't understand, it's in your lab, it's pointing in some direction, because the quantization axis over the 375,000 times per second, the quantization axis rotates around. The quantization axis dotted into a DC field, a magnetic field, averages very, very precisely to 0. So if we apply a transverse, even a very large transverse magnetic field, we don't see the frequencies of our experiment move very much, except in the following case. This is meant to be the electric field in the x direction, electric field in the y direction, and it rotates in this Lissajous figure 375,000 times per second. And it averages out the effect of any stray magnetic field in the lab. If instead, so basically we're driving the x field as a cosine and the y field as the sine. If the field in the x direction has some second harmonic on it, so it's not varying purely sinusoidally, but with a second harmonic, which it surely must, because these are relatively large voltages and we're putting them through an op-amp, and all op-amps at some level are nonlinear, then the Lissajous figure will look a little bit like an A. It'll have a pointy side and a flat side. And if the pointy side is going in the same direction as the magnetic field, we will see a Zeeman shift. This turns out, for subtle reasons which I won't go into right now, to be our single most troublesome systematic error these days. We spent 6 months thinking about this. We now have it well under control, but it was not simple to understand the effects of this on our experiment. We can also move the ions by applying DC voltages on the electrodes. We can move the ions around in the trap side to side. This is moving it in these sort of X direction. These different lines correspond to different Z positions. We see some frequency shifts. We have to understand them. We do. We take our data blind. Like so many precision experiments, we're very nervous about not so much fooling the rest of the world, but fooling ourselves. We think of ourselves as honest people, but we're subject to the same psychological biases as anybody else. So the computer lies to us. It collects all the data, and to just the single frequency combination, which tells us the electric dipole moment, it adds a random number, and it's been the same random number for a year, but the computer won't tell us what the random number is. So when we take a measurement, we don't know where we're at, but we can take our data, we can subtract the average from it, and we can see that things fall very nicely. We had nice sort of statistical Gaussian distribution, and we can, from this determine what our statistical precision is and see where we're going to show up. Decide what our errors are going to be before we know what the central value of those error bars are applied to. Here's a sort of historical plot showing measurements of the electric dipole moment over the years, going back to 60 years now or something like that. These are the measurements of Larry Hunter, who did experiments in a vapor cell. These are the experiments of Gene Cummins. And this was sort of the last experiment to be done on atoms. It became very, very difficult to do a better experiment on atoms. The people at Imperial College, Ed Hines and people who followed after him, have always been champions of using molecules. And they did the first serious measurement in a molecule, and we were able, using a molecular measurement, you can see they quickly made progress and were able to make the best. For a while, they had the best possible measurement. The Acme group made a much better measurement, about a factor of almost 20 better. We came into the business with our own molecular experiment, and the first generation experiment, which we finished now 6 years ago, enabled us to almost tie the Harvard-Yale group. So we felt very good about that. We felt like, well, we may be the second best electric dipole moment measuring experiment for the electron, but we're pretty close. But then the Harvard-Yale or the Acme group did something really mean, which is they did a factor of 10 better. This was just about 3 years ago. And okay, well, we thought that was just plain rude. That was so unnecessary to, flex on us, you might say. But we decided that we're now finishing our second generation experiment. We are most of the way through our final data run. Our current statistical sensitivity works out to 2.5 times 10 to the minus 30 centimeters. We anticipate getting down to somewhere around 2 times 10 to the minus 30 centimeters. There'll be some systematic addition to that, to those error bars as well. And all those will be decided on before we unblind and find out, this is just everything referred to the mean. But that mean is, we don't actually know what that mean is in real numbers until we tell the computer to unblind. That will be a very dramatic moment. And it will happen. We don't know what the central value is, but we should have a result to report later this summer, perhaps as soon as August, but certainly by the end of the summer. So that's coming very soon. When we do, we anticipate, we'll see, but we anticipate being a little bit more accurate than the current Acme group experiment. And then just to sort of finish up my talk, I'm going to tell you about what we call our third generation experiment, which we hope to be almost another factor of 10 better. Although it's now quite a ways out, it won't be, that experiment won't work for at least another 4 years, I would say. So how are we going to do better? Okay, the second generation experiment is going to be announced later this summer. The third generation experiment is under construction and actually some preliminary debugging. We're going to change our atoms, our molecule species from hafnium fluoride plus to thorium fluoride plus, which gives us an enhancement of the internal electric field by a factor of 1.5. Not earth-shattering, but helpful. The most important thing about thorium fluoride plus compared to hafnium fluoride plus, or compared to thorium oxide, the state in which the Acme group works, is that in thorium fluoride plus, the triplet delta 1 state, the science state, the state which has this the very enhanced electric field and which has the omega doublet, which makes for convenient measurements, that state is the true electronic ground state of thorium fluoride plus. So there's no obvious limit to coherence time. In all the other experiments, in the Acme experiment and our hafnium fluoride plus experiment, it was forbidden, but there was some spontaneous emission, which meant that, for instance, the hafnium fluoride plus experiment really can't go beyond about 3 seconds. The thorium oxide experiment in Acme really can't go beyond perhaps 3 or 4 milliseconds. So that will we hope to take the coherence time from 2 seconds out to about 15 seconds. We'll have to work much harder on field homogeneity, and we'll have to provide some black body shielding. There'll be some cryogenic aspect of the experiment because molecules, unlike atoms, molecules will absorb black body radiation. So we need to operate in a cold environment. Our initial thinking was going from 2 seconds to 15 seconds was not such a big win. It only because yes, our line is 15, smaller by a factor of 7.5, which is helpful. But if you're working in a trap, if you take 7.5 times more time between your Ramsey pulses, it means you can make 7.5 times fewer experiments in a given hour. So that goes as the square root, and you might think that your overall statistical sensitivity in, say, an hour of data is going up only as 15 over 2 to the half power. So maybe only a factor of whatever that works out to, a factor of 2.5, which would be disappointing. We're hoping to get around that by doing, we call it multiplexing or parallel processing. Our jargon is the bucket brigade. We have all the state preparation. We at one end of the experiment, we put it into a series of Powell traps, which are actually moving along like a conveyor belt, like someone passing a bucket from one person to the next person to the next person. And while it's passing along, they're moving along here through the cryogenic shield, through the magnetic shield. The internal phase, basically right here, we apply a pi/2 pulse. Now they travel along, the phase evolves, and when they get here, we'll apply another pi/2 pulse and then do the readout on this end. So at any given time, we'll have an atom which is 1 second, 2 seconds, 3 seconds, 4. This is just conceptual. There'll probably be something like 20 or 25 buckets of ions evolving at the same time. And it's not crazy to have 25 separate ion traps because almost all the expense and hassle of making an ion trap is in the state preparation, where you have to have lots of lasers, and the state readout, where you have to have lots of lasers. And those are very expensive, but we do each of those only once. In between, we just have very low tech. These are basically sheet metal ion traps that are floating along here. Here's a design of the experiment. These are, from the side, you see a series of discs. Here are the discs. These rods here, which run the length of the experiment, provide the rotating electric field. Here's the vacuum chamber. This is actually still as large as this vacuum chamber is, this is still only we call it the prototype. We sometimes call it the baby bucket brigade, or baby bucket for short. But the baby bucket will sort of run the length of this part here. Here's Sun Yul Pak putting the ion trap. You can see the series of electrodes here, sliding it into the vacuum chamber. We're about to seal it. And then the good news is that just as of I think only 8 days ago, we saw our first ions in the 3rd generation experiment. It's a long ways from making a precision experiment, but here they are at a position sensitive detector. And you can see the ion cloud is kind of ugly for reasons we don't understand, but we're only 1 week into it. So that's where we're going with this experiment. And I think that will probably be serious science from that, could be 4 or 5 years out. But we're optimistic that it'll be at almost another order of magnitude to the current limit. And with that, I'm going to pause and thank you very much for your attention. And my understanding is that people are able to, if you put questions into the chat, people will be able to read those questions to me. Thank you.